invitation and thank you for coming. So the plan is to discuss some recent results on the boundedness of varieties of general type that in particular lead to the construction of the corresponding moduli spaces. Most of what I will discuss is recent work joint with James McKernan and Chengyang Xu. So the subject is very technical, so I'm going to try to give an overview of the main ideas that go into the solution to this problem and to try and give an idea of every single step without hopefully getting too much bogged down by the technical details. Some of the computations are really quite involved, so maybe they're better done in the privacy of one's office, but so sometimes I'll make some simplifying assumptions so that we can more easily digest the important ideas. I was also warned that there were going to be a variety of levels, so I will start with an introduction, things that will be well known to more senior people. I see a few senior people. I apologize to them if they get a little bored during the introduction. And then probably by next time I'll get through some of the technical prerequisites. I will remind issues about multiply ideal sheaves and singularities of the minimal model program and some vanishing theorems. And probably, hopefully by the end of next time, start getting to proofs of some of the actual statements. So let me start with a general introduction and motivation for the problem. I am preparing notes, and I will post them, hopefully on my webpage if I can figure out how to connect to my webpage and do this remotely, and otherwise I'll find another solution and let you know next time. So as you know, in algebraic geometry, one of the main goals we would like to do is to classify algebraic varieties. So let's, for now, to fix the ideas, consider complex projective algebraic varieties. So throughout these talks, I'll always be working over the complex numbers, or at least a field of characteristic 0. And let's make the assumption for now that X is smooth. And very soon, we'll decide that maybe it's not the right thing to work in the smooth category. So how do we study these objects? Well, you usually study geometric objects by looking at functions on them. But of course, if you look, this is compact, so if we look at global holomorphic functions, that's not very interesting. You just get a copy of the complex numbers. You get constants. So that's not going to be interesting. So in order to effectively study these, we need a line bundle. Or equivalently, we need to look at meromorphic functions with certain prescribed poles. And finding interesting line bundles in general is not easy. There's usually only one choice for the line bundle that you want to use. That's known as the canonical line bundle. So you can think of the canonical line bundle as given by the top exterior power of the cotangent sheaf. So in other words, this is locally defined by sections of if x1 through xn denote local coordinates, then it's locally generated by this symbol. And here I'm using n to denote the dimension over the complex numbers of x. So let's start by the simplest example that we're all familiar with is the example when the dimension of x is equal to 1. Then topologically, we're talking about Riemann surfaces, so these are classified by the genus, which is just h0 of omega x. So by little h0, I denote the dimension over the complex numbers, of course, of the space of global sections. So now there's sort of three general subclasses. So you're probably all familiar with this. I'm just setting things up for the higher dimensional cases. So when the genus is 0, then we only have one interesting example, projective line, and the canonical line bundle does not have many sections. It corresponds to homogeneous polynomials of degree -2. So H0 of omega x is not interesting. Again, when the genus is 1, now we're talking about elliptic curves. You can think of these as the complex plane quotient out by a lattice. The way the lattice sits into this complex, in the complex numbers, tells you what elliptic curve you're dealing with. And here, the canonical line bundle is again not interesting. It's just a trivial line bundle. We don't have interesting sections. However, we do have a one-dimensional modular space, one-dimensional moduli space of elliptic curves. So even though topologically these are all isomorphic, from an algebraic point of view, they're not isomorphic. There's a one-parameter family. Now, the case that I'm most interested in, this is the case of general type. So for genus greater or equal to 2, we say that we are in the general type case, most curves, so to speak. Then, in this case, the canonical line bundle has degree, positive degree. So the degree of the canonical line bundle is 2g minus 2. This is always true, but as long as g is greater or equal to 2, this is a positive number. So in particular, the canonical line bundle is ample. And in fact, we'll see, it's an easy computation. The third tensor power of the canonical line bundle is very ample, which means it gives you have an embedding of x into the corresponding projective space. Okay, so from a notational point of view, maybe I will often denote this simply by h0 of 3kx. So kx is the divisor corresponding to the zeros minus the poles of a meromorphic section of the canonical line bundle. Often it's referred to as the canonical divisor, but there is no unique choice. There are many canonical divisors. Okay, so the interesting fact here is that we have, there is a 3g minus 3 dimensional moduli space. Let's denote it, I don't know, by m sub g. Now, this moduli space it's irreducible, it's smooth, but it's not compact. But the nice thing is that it can be compactified in a geometrically meaningful way. So, to compactify, so we want to find the projective variety. We need to add some extra points, and these extra points correspond to the so-called stable curves. We must include stable curves. So these curves are no longer reducible curves. They could have more than one component. So it's no longer a smooth curve. But if I take the normalization, say f, let's say y is the normalization, has more than one component, then, or maybe I should be a bit more precise. So what are the allowable singularities? So singularities are nodes, and if f from y to x is the normalization, so now when I normalize, I get components, say y1 or y2 or several components. Each component is now a normal curve, so it's a smooth curve. And if I take the pullback of the canonical line bundle of x, So it's not 100% clear what the canonical line bundle of X is, because now we have singularities. So I can't just say take the top exterior power of the cotangent sheaf, but we'll discuss that later. It still makes sense to talk about the canonical bundle of X, because we made some hypothesis on the singularities. And if I pull it back and restrict it to a component yi, then I'll get an expression of the form omega. Let me improperly just write kyi plus delta I. So I'm informally switching from line bundle notation to divisor notation, right? So I'll do this all the time. So now the key point is that in order to be a stable curve, we must require that this Smith's gadget, so you think of these as sections of the canonical bundle that are allowed to have a pole along the divisor delta I. This divisor delta I corresponds to the double locus. So if these two curves meet at a point, then the pre-image of the point will give you divisors delta 1 and delta 2 on the two curves. And so this mixed object is going to be ample, which in the case of curves, again, just means that it has positive degree. So that's what a stable curve is. And adding stable curves allows you to compactify this modular space. And at first, this is somewhat worrisome because we've now included singularities. But you can think of these stable curves as being built out of usual smooth curves by gluing along the double locus. And there's a way to make this precise. And so then it looks much more friendly. The caveat is that you have to be willing to work with sort of these mixed objects, these pairs, consisting of the canonical line bundle and a divisor. So we would like to sort of repeat this in all dimensions. That's the sort of the goal, the overriding goal. So let me make a definition. So I've tried to stress that the canonical bundle, the top exterior power of the cotangent sheaf, plays an important role. It's the only line bundle that you really have working for you, and that in some cases it provides little or no information, but in most cases it seems to provide a lot of information. So let's formalize this with some definitions. So by R omega x, or sometimes R of kx, I'll denote the canonical line, the canonical ring. And this is just a graded ring where each graded piece is given by the sections of the corresponding tensor power of the canonical line bundle. This is their example, all m greater or equal to 0. And this is what we call the canonical ring of, let's say, a smooth complex projective variety. But yes?
Do you allow the nodal curve with self-intersection? Stable curve.
Yeah, why not?
Okay.
Yeah, but yeah. Anyhow, there are some issues, yes. Okay, yeah, so this is the canonical ring, and this is going to play an important role for us. In particular, it allows us to define certain birational invariants. So by kappa of x, we denote the Kodaira dimension, and this has several equivalent definitions. So one definition is the transcendency degree over the complex numbers of the canonical ring minus 1. So from this definition, it's this transcendency degree is always greater or equal to 0, so it could be minus 1, 0, 1, all the way up to the dimension of x. So in the case of curves, these are the subdivision into the three possible Kodaira dimensions. Kodaira dimension minus 1, 0, and 1. Then equivalent definitions for the Kodaira dimension are the maximal dimension of the image of x under the mth canonical, the maximum of the set of dimension here, m is greater or equal greater than 0. So what does this mean? This map phi mkx is the map induced by sections of the nth tensor power of the canonical bundle. So if h0 of omega x to the tensor m has a basis given by sections, let's say S0 through Sn, then phi mkx will be a rational map defined from x to the corresponding, maybe capital N here, corresponding projective space defined by sending the point x to the ratios S0 of x, S1 of x, Sn of x, big N. And I've drawn this as a broken arrow because it's not defined on some points. It's not defined precisely on the points where all of these sections vanish. In other words, it's not defined on the base locus of this multiple, the canonical line bundle. So this is an equivalent definition of the transcendency degree. And this case here plays an important role. So if the quadratic dimension of x is equal to the dimension of x, then we say that x has general type. So the typical example is curves of genus at least 2. And since this is the case that we're going to be dealing with most of all, let me make a couple more observations. So let's say note that k of x is equal to the dimension of x. This is equivalent to several other facts. So it's equivalent to the nth canonical map being birational for every m sufficiently big. See, this equivalent condition definition for the quadratic dimension just says that some multiple gives you a map, the image has the same dimension. So it gives you a generically finite map. Here, I'm actually saying that the degree of this generically finite map is 1. Right? So it's birational. It's an isomorphism on an open subset. And that works for all m sufficiently big. And another equivalent definition, these are not too hard to check, is that we can write that kx is Q linear equivalent to an ample plus an effective divisor. A is ample, and E is effective. So, should also ask you to please interrupt and ask me for clarifications if I use some terms that are not familiar to everybody, or make some mistake, or say something confusing. So far everybody's happy? Okay. So another equivalent, the last equivalent one, condition that I want to remind you of. So this is equivalent to the volume of kx being positive. So the volume, what is the volume of k of x? Well, this is just the limit as m goes to infinity of h0 of m k of x divided by m to the n. Remember that n is the dimension of x over n factorial. Okay, so it's not immediately obvious even that this limit exists. It's a theorem that the limit exists. It's not a very difficult theorem, but it's a theorem. If you don't know the theorem, then you would define it as the lim sup of these quantities, but it's actually just a limit. And so, for example, if k of x is ample, then by self-vanishing, this group H0 is computed actually by the Euler characteristic, and using Riemann-Roch, then you can see that the volume of k of x is actually just equal to the top self-intersection of the canonical divisor. So, for example, if the dimension of x is equal to 1, it's an easy exercise to check that the volume of kx is 2g minus 2. And yes?
This theorem that you can replace the lim sup by lim. Is this specific to the canonical bundle, or can you do it with any line bundle?
Okay, so it's a relatively easy theorem that you can do it for any line bundle, and it's a recent result due to, well, recent as in the last 5 years, due to Kovansky and maybe somebody else, I unluckily don't remember, which is non-trivial, that it actually works as a limit for all m sufficiently divisible in intermediate quadratic dimension. So it's not really specific about the canonical. But to state it right, there are some small subtleties. Okay, so of course, in high dimension, the picture is going to be much more complicated. And problems already start in dimension greater or equal to 2. So there are many problems, many technical issues if the dimension of x is greater or equal to 2. Most of the issues stem from the fact that in dimension greater or equal to 2, two birational varieties are not necessarily isomorphic. So even with a surface, you start with your favorite surface. X is a surface. You pick any point, and you can just blow it up. You produce another surface with some exceptional divisor, which in this case will be isomorphic to P1, and you can keep repeating this. And so on. So this clearly is going to cause problems because I can do this infinitely many times, and these will not be topologically equivalent. So the second Betti number, for example, will change. So they really can't belong to the same component of the moduli space. So it's clear that more care will be necessary. And in fact, I think in dimension greater or equal to 3, it's not even clear if, for example, your topological type will distinguish between the various components of the moduli space. So could you have infinitely many components of some moduli space with the same topological type? It doesn't seem obvious to me. But here's another problem. For surfaces, you can get around that by looking at the second Betti number. Right? That's an invariant that can tell the difference between a surface and its blow-up. However, there's another problem.
I'm sorry.
Yes?
Could you repeat that again? In dimension 3, what is not clear?
Okay, so vague question that suggests that things might be difficult. Okay. I'm not claiming any theorem of any kind. So question. Is it possible that there are infinitely many surfaces of general type that are topologically equivalent, not surfaces, varieties, surfaces, I know how to answer the question, that are topologically equivalent, but not deformation equivalent. Right, so if we do succeed in constructing a moduli space, we would like this moduli space to be at least of finite type of the complex numbers, and preferably we would like it to be compact, projective. Right, so this is one of the things that we would like, right? Once you have it, then you can deform one. If they belong to the same component of the modular space, you can deform one into the other. But if it's going to be of finite type, then it should have only finitely many of these components. So the topological information allow you to distinguish, to play the same role as the genus, right? So these modular spaces have infinitely many components, but we can tell them apart with this discrete invariant, the genus. Does the topology work for, even for threefold? It doesn't seem to be obvious to me. Here's another problem that I can actually write down an example to show that we cannot just consider surfaces of general type. So if you just consider the space of all surfaces of the general type, you'll get something which is not separated. Okay, so surfaces of general type give a non-separated, let's just say issues. I haven't defined a modular space, so I can't show you that the modular space is not separated, right? So how does this issue occur? Well, suppose fix some threefold mapping down to a curve. Let's say that this is a smooth morphism from a threefold to a smooth curve, maybe an affine curve. And let's assume that we have three sections. So this contains, let's call them C1, C2, and C3. Three sections meeting as transversely as possible at one point. So let me draw the picture to show to you. So this is your curve C. This is a point, say, O. And we have many fibers. And maybe it's a smooth map. So all of the fibers are topologically equivalent. Maybe you can just even take the product. And you take these three sections, which are meeting as transversely as possible at one point. So that any two of them will have a different tangent direction at the point. C1, C2, C3. Now, what you want to do is you want to consider new threefolds. Y1 will be the blow up along, well, you start, I'm going to take three blow ups. So I start by blowing up X along this section C1. Then I blow it up along the strict transform of C2, and then along the strict transform of C3. Or I do this in a different order. Now, for any point on my curve, which is not this special point O, we have the fact that the fiber, the corresponding fiber over the point P will be isomorphic. If I have three distinct points, it really doesn't matter what order I blow them up in. However, over this central point, since I'm blowing them up in different order, I actually get non-isomorphic. Surfaces. So if there were a modular space parametrizing these surfaces, it would have to be non-separated. So this is an issue. So the solution to this problem is to work with surfaces up to birational automorphism. This is an old solution. The Italian School of Algebraic Geometry already did this. Work with surfaces modulo, let's say, up to birational isomorphism, or surfaces or higher dimensional varieties. Let's call them n-folds. And in fact, it's even slightly better. In each birational equivalence class, as long as your varieties of general type, you can fix a distinguished representative. So if X has general type, then each birational class has a distinguished representative. And this distinguished representative is called the canonical model. So how's the canonical model constructed? It relies on the following result. So there's the following theorem, which is due to Birkar, Cascini, Hacon, and McKernan, and also to Sewell, which states that suppose that x is, for now let's assume, because I haven't defined the singularities of the minimal model program yet, so let's say n is smooth, projective, let's just say complex projective, smooth variety of general type, well, we don't need a general type, then the canonical ring k of x, which I just defined, the one whose graded pieces are sections of multiple of the canonical line bundle, is finitely generated.
Can I be a pain in the ass?
Sure.
Even though you are saying y10 is not isomorphic to y0, you did write isomorphic, so that's not.
Thank you very much. Yeah, that's not being a pain, that's being helpful.
Sorry about that.
That's being helpful. Thank you. Yes. I mean, I don't want.
No, you are saying it's not isomorphic.
I know, I said it, but there's a bit of dyslexia
Sorry about that.
in there. Okay, so getting back to this issue, this canonical ring is finally generated. So if the dimension of x is equal to the quadratic dimension of x, then we have that the dimension of, so first of all, proj of R of kx makes sense. This is a finitely generated ring, so you can think of proj just as being given by the generators and relation amongst this graded ring. And by definition of the quadratic dimension, the dimension of this guy will be equal to n, which is, my assumption is that I'm using n to denote the dimension of x. So we call this, in this case, in the case of general type, we'll call this the canonical model. And actually, so in fact, we get a birational map. So what is this birational map? Well, this ring, so say that R of kx is generated in degree k. So what do I even mean by this? You have to be a little bit careful, right? This is going to be generated in degree at most something, right? So maybe we consider the subring where instead of looking at all positive integers m, we look at all positive integers m that are divisible by k, which is generated in degree 1. So let me just be, as not to waste too much time being ultra precise, let's assume that this is generated exactly in degree k, then this map here, then this map is just given by phi k times k of x. Right? If this were generated in degree k, then all the important information is trapped by h0 of k times kx, and then that map precisely corresponds to this one. So that's a birational map. And the important thing to notice is one of the problems, one of the things that make this theory a little bit hard is that we land outside of our category. We now are dealing with singular varieties. So x canonical is not necessarily smooth. Sometimes it could be smooth, but that's rare. But it has canonical singularities. We'll talk about these soon. I'll define them soon. And the important fact about canonical singularities is that they are mild. These are mild. How are they mild? Well, they're mild in several ways. The most important way in which they're mild is that we have vanishing theorems for varieties with these singularities. But let me tell you one way that's in which they're obviously mild. So they're sort of, these singularities are cohomologically insignificant in the following way. So e.g., they have rational singularities. So So if, let's say, f from y, so if this is a morphism from a smooth variety, a birational morphism from a smooth variety, then all higher direct images of the push forward of the structure sheaf of y are 0 for every I greater than 0. I should also mention that this is a normal variety, so f low star of O of y is equal to O of x canonical. So in other words, from a cohomological point of view, they behave like they were smooth. So many of the cohomological computations that we have to do are very easy to do on, on canonical models, and in general on varieties with canonical singularities. But I'm still in the introduction, so I'll talk about what the actual definitions of these singularities are later on.
You mean proper Russian?
Yes, otherwise, yeah.
Sorry.
Yeah, that's
I
yeah.
apologize.
Okay. Now, another feature is that canonical models are unique. Why they're unique? Well, there's a formula for it, right? It's given by proj of something, by proj of the canonical ring. The canonical ring is a birational invariant, and so it's uniquely determined. So canonical models are unique, and this gives us the expectation that the modular spaces should be separated. We still don't expect that modular space will be proper, because even in the case of curves, you have to allow stable curves which are not normal varieties. So this would not give you, certainly cannot give you a proper modular space. So what do we need to do in order to make the modular space proper? We need to add what are known as semi-log canonical models. So to produce a proper modular space, we'll have to allow what are known as semi-log canonical models, nothing to do with Salt Lake City. Semi-log canonical models. So what are semi-log canonical models? So maybe let me give a quick definition. So X is a semi-log canonical model. So of course I'm going to insist that if it is projective, it's not necessarily going to be normal, but it will be sort of the next best thing to normal. So it will have simple normal crossings, singularities in codimension 1. So it has nodes as singularities in codimension 1. At codimension 1 points, it looks like smooth hyperplanes meeting transversely. I'm going to insist that it be S2, so the depth of each local ring is greater or equal to 2. This is sort of telling you that you can extend functions from an open set, where you've only thrown away a closed subset of codimension greater or equal to 2. You can extend functions from a big open set. So for many things, you can work with these just as if it was a normal variety. And we need to require that K of X, the canonical line bundle, the canonical, it's no longer a line bundle, but it's at least a Q line bundle. It's Q Cartier. Some multiple of this is a Cartier divisor. It corresponds to an actual line bundle. And ample. so this is actually not quite enough to declare this to be a semi-log canonical model. We have to say a little bit more about the singularities. So just as we had before, if y to x is the normalization, and if on each component of y, I rewrite the canonical line bundle, so I pull back the canonical line bundle and restrict it to a component yi, then I'll get one of these mixed objects, k of yi, this is now a normal variety, plus a divisor delta I, which keeps track of the double locus, then we need this to have log canonical singularities. We need that to also have mild singularities. And I have not defined this yet, but I will define it fairly soon. So let me just stay in the introduction. So there is some additional condition that I need to eventually discuss.
When you say simple normal crossing, this excludes self-intersection of a component? It's simple. I always get confused.
No, I don't think that you have to. You're gonna.
Is there a difference between normal crossing and simple?
So I'm bad at remembering. Yes, and that's precisely the difference. You know, you do one. I'm bad at remembering what the official name is, but Fujino certainly remembers.
Normal crossing is sufficient. Yeah.
The normal crossing is allowed.
Yeah.
So officially, in the definition of semi-log canonical models, do we allow normal crossings?
Yes.
Yes, that's what I thought. So I should really say normal crossing here. You're absolutely right. Now, you can always make it simple normal crossing, but then you'll have some component over which this gadget is no longer ample. Okay, so morally speaking, you should always think of these semi-log canonical models as being built up out of these components yi, which are being glued together along the double locus. And so most of the questions that you have actually become questions just about log canonical pairs, log canonical models.
Is the Salt Lake City model equivalent to saying you have smooth varieties of general type, fiber over curve, texture curve, and then take the semi-stable model?
I don't know if it's equivalent, but they certainly arise that way. So let me.
So are there any SLC models that cannot be smooth?
Smooth, yes, certainly. There are components of the moduli space that do not contain any smooth points. This is correct.
Oh, I see. Oh, that was the question.
Right. So you're thinking about Carroll's work probably on the boundedness, where he assumed he did it for smoothable. But there definitely exist components of the moduli space that are not smoothable. So that is one of the issues. We have now enlarged our category. Have we enlarged it too much? Have we lost, track of anything reasonable? We started with smooth varieties, then we decided that we had to buy canonical singularities, and now I'm telling you that you also have to buy semi-log canonical models, semi-log canonical singularities. And then I casually remarked that some of these semi-log canonical models don't even come from specializations of canonical varieties, right? So, it seems like the problem has gotten much harder. Now, I'll try later on to convince you that really, first of all, you should think of them as given by gluing together these objects, which are relatively natural, and it doesn't really add more complexity to the situation. If you can deal with log pairs, then you can deal with semi-log canonical models. And one other remark is that, where should I make it? Maybe here.
I have one more.
Okay, go ahead.
So this SLC model is still canonical model of some simple normal crossing variety.
Yes? Yeah. So, but I would prefer to focus on the component. So if I look at this, then it is the log canonical model of this guy itself. Right? That has log canonical singularity, and if you take proj of its ring, that's it. So later on, we will also consider pairs of the form x, b, where b is a sum of bi, bi, and we have to allow more interesting coefficients. For example, bi coefficients of the form 1 minus 1 over n. The reason for this is that when you're proving something by induction of the dimension, you have to use a tool called adjunction because of induction class adjunction. So when e.g., so if you have an ambient variety, let's say y contains x, so this is a smooth divisor in a smooth ambient variety. Then when you restrict the canonical class of y plus this reduced divisor to x, you just get the canonical divisor of x. You're taking residues along this pole.
What do you mean by the condition on bi? The numbers bi?
Oh, so the numbers bi, these are rational numbers. Maybe n is a very poor choice. Let's use k, where k is any positive integer. So they're rational coefficients which don't even belong to a finite set. They belong to an infinite set, but a not too threatening infinite set. Okay, and so when you adjunction from a smooth variety to a smooth divisor is a very friendly operation. However, but if, say, the pair yx has log canonical singularities, which I haven't defined yet, I will get to it soon, then ky plus x restricted to x is of the form kx plus a divisor, a sum of bi, bi, let's say, where these bi's are in the set 1 minus 1 over k, k in n, union infinity. You also have to allow the divisor 1. So I haven't defined log canonical yet, but I'll get to it soon. So unluckily, I'm giving you a warning that I will need to allow not just coefficient poles with order 1, but up to replacing by a multiple, I need to allow poles with rational coefficients. Okay.
Is that assumption just for simplicity or
Which assumption?
this one? We will consider pairs and you're putting the condition on the coefficients. So is that for simplicity we will only consider those pairs or?
I'll state a more general theorem where I allow more general coefficients.
So your theory will apply to any coefficient?
Yes. With some technical condition on the coefficients, which I will explain later. But I think this is the minimal set of coefficients with which you can get away. You might be able to set up a proof by induction just using these coefficients. Those are the unavoidable ones. Okay, maybe I should give the intuition why the modular space at this point should be proper. Moduli of semi-log canonical models. So you start by considering a family of semi-log canonical models over some curve, some affine curve maybe, which is where we've removed a point. So if, let's say, P is in C0, then I insist that the corresponding fiber, x0p comma b0p, is a semi-log canonical model. So it may not be normal, but it has mild singularities, and the canonical class is ample. Okay, so maybe I don't need to put a boundary here. Okay. Semi-log canonical models. Now, valuative criterion of properness, you would want to be able to sort of add a special point in and complete this family in a unique way over that point. So let's pretend that this is contained in a curve C. So in fact, C0 is just C minus a special point O. And I want to compactify this family in a unique way such that special fiber is also a semi-log canonical model. Now, there is one obvious problem, is that the way your family degenerates, the special fibers may not be reduced. And this happens in practice. So what we do is you begin by taking some compactification, just some, this is a, I'm assuming it's a projective morphism, so I can take a compactification which has horrible singularities over the origin. And now I can take the resolution of this compactification, but in doing so, the central fiber may have many non-reduced components. So we apply semi-stable reduction and resolution of singularities to produce a new family, let's say x tilde, b tilde, with what properties? So this new family is going to be, this new family is birational to the family that you obtain simply by base change. Okay. I put the B0 in there, so maybe let's keep it. It's going to be smooth, but the extra thing that I can achieve by semi-stable reduction is that the central fiber is reduced with simple normal crossings. Now I really mean simple normal crossings. So the central fiber is a union of subvarieties of dimension 1, which each one of them is smooth, and they meet transversely. So now, yes?
I'm a little bit worried. Like, if you start from the situation where the general fibers are singular, so then you have to blow up there.
I'm not claiming that the general fibers are isomorphic.
I understand.
Okay.
But the general fibers, when you blow up there, you might be producing some non-reduced guys. And even if you take the finite cover of C, those non-reduced guys will not be killed at the central fiber. If you have a smooth fiber, then semi-stable reduction can be obtained after taking finite cover. But if you start from some singular guy, and if you have to blow up...
So I think you worry too much. So those on the general fiber,
yes.
Those things that you're claiming are non-reduced, they're only non-reduced in terms of the coefficients that you get when you compare the two canonical divisors. But when you blow it up, you can actually get, say that for simplicity, we only have that the general fiber is at least normal.
Ignore me. I will talk with you after the lecture. Yeah, sorry about that.
So again, this is still part of the intuition. I haven't made any precise statements about what log canonical models we can produce and so on. Yeah. I'm just trying to give an intuition of why these semi-log canonical models should give you proper space.
Yes.
So now, the compactification is given by simply taking the corresponding, what we call log canonical model. So you take proj of the ring corresponding to k x tilde plus b tilde. This is, again, the graded ring. Each graded pieces corresponds to sections of m times the canonical class plus b. This should be the ring over C tilde, of course. And so this maps down to C tilde. This is isomorphic. And now, with this choice here, the general fiber of this morphism is actually isomorphic to every fiber which is not over the special point 0. We have isomorphism between those fibers. And the central fiber is automatically a semi-log canonical model. Maybe the one thing to observe is with this choice here, the central fiber is just given by proj of r of k x tilde 0 plus the corresponding guy. So the way the theory is constructed, this automatically will have semi-log canonical singularities, automatically will have ample canonical class and satisfy all the conditions that we need for a semi-log canonical model. Yes?
As a stupid question, is that the B is still hold in the same way, the one minus?
Oh, the coefficients?
Yeah, is B is still hold in the equations is still 1 minus?
You have a good point, and I'm going to do, when I actually get to the part where I actually do proofs, I am going to do proofs like that, which tells you why the coefficients are still the coefficients that you want. It's a easy but non-trivial issue, what you mentioned. So yes, I'll get to that. Okay, so this is just intuition. This is kind of the idea of why I haven't. This is not a proof of anything. This is just once you know that canonical models exist, there's sort of a natural way after base change to compactify the family, just by virtue of the fact that this ring is finally generated. Okay, so 5 more minutes of hand waving, and then I will get to actual definitions and actual proofs. So I just wanted to say one more word about how, what is the precise kind of technical result that you need to do, you need to prove to actually construct the modular space, and give you a vague idea why. I'll mention the word Hilbert scheme. There's a book being written by Collard on the subject, and this criterion will be mentioned in the book explicitly. And it's already explicitly mentioned in one of his survey papers. So, as we know, in order to construct a modular space, we need to fix certain invariants. So what's the typical invariant that we fix? It's the corresponding Hilbert polynomial. So we fix a polynomial, a Hilbert polynomial, let's say h sub t, and we consider semi-log canonical models such that, let's say, for some fix a polynomial, and let's also fix an integer m, positive integer, and then we consider semi-log such that mkx is actually Cartier. It's actually a line bundle. So our hypothesis is just that k of x is a Q Cartier, an ample. So now mkx becomes actually an actual line bundle. There exists some such multiple. We don't know how big this m is. And is Cartier and very ample. So sufficiently, by hypothesis, there always is one such m, but we fixed the m. So maybe this m does not work for all semi-log canonical models. And we want to look at those semi-log canonical models such that the dimension of the number of sections in multiples of this Cartier divisor is actually equal to the given Hilbert polynomial. Okay? So maybe if you want to be on the safe side, maybe you'll also assume that higher cohomology vanishes so that this is equal to its Euler characteristic. Okay, so then, now, note that we have an embedding phi mkx from x embeds into the, because I've assumed it's very ample, embeds into the corresponding projective space. And under this embedding, we have that Ox mkx is just a pullback of O Pn1. So the idea behind constructing a modular space is, first of all, we want to identify, let's call it SHTM, contained in the Hilbert scheme of the corresponding Hilbert polynomial of Pn. So here there's an M. I guess. So we want to look, we want to identify the locus that corresponds to these semi-log canonical models with the property that mkx is Cartier and very ample. So it should be at least a subset of the corresponding Hilbert scheme. And we would like to prove that this is, what we want is that this is a locally closed subset. And then for our moduli space, what we want to consider for our moduli space is given by taking this locally closed subset and quotienting out by the corresponding automorphisms. Now, this can only work if we can find a uniform M such that for any semi-log canonical model with this Hilbert polynomial, mkx is Cartier and very ample. This strategy works if there exists such an M which depends only on the Hilbert polynomial. So I'm not discussing any of the details. There's a huge body of work that goes into actually constructing this modular space. For example, you have to check that this is a locally closed subset of the Hilbert scheme, and many, many other details. And there's been work by Kolar, by Vivek, by Fugino, Kovac, Patakvalvi, Alexev, and many others on this subject. So I'm not actually discussing in detail how to construct the modular space, but I hope that it is clear that finding a uniform M such that mkx is Cartier and very ample is one of the key issues in constructing this modular space. And in fact, in dimension 2, this was solved by Alexev. So Alexev proved the necessary boundedness result later with some improvements in a joint paper with Mori as well, Alexev Mori. So let me now state the precise theorem that I would like to look at. This theorem is due to myself, James McKernan, and Chen Yang Su. So we're going to have to fix some data. We won't fix the Hilbert polynomial, but we'll fix n, that stands for the dimension, and we'll fix a constant c greater than 0 that stands for the volume of our canonical model, which corresponds to the leading coefficient of your Hilbert polynomial. And we'll also fix a coefficient set c. So this is going to be, let's say that it's contained in 0, 1, and is a DCC set. So the typical DCC set is the set of standard coefficients, 1 minus 1 over k, where k is positive integer, possibly infinity. In general, what does DCC mean? DCC means that for any non-increasing sequence is eventually constant. So a DCC set will have accumulation points from below, but no accumulation points from above. Okay, so we fix a DCC set, and then we look at the following set. So we look at the set of all possible semilog canonical models with the fixed data. So these were semilog canonical models, which depends on the dimension, on the volume, and on the coefficient set. So these are X has X and B. B has the form sum of BI, BI, such that these are semilog canonical models. Remember, semilog canonical model means it's possibly reducible, but it has mild singularity, and the class of kx plus b is an ample Q-Cartier divisor. The dimension of x is equal to n. This means every component has dimension n, of course. Kx plus b to the n is equal to c. And these coefficients bi are in my nice coefficient set. Then this is bounded. What does bounded mean? Let's say IE has finitely many deformation types. So there exists a scheme. Well, let me sort of use a pair notation again. So this is a finite type over a base S, which is again, so this is a projective morphism over a scheme of finite type over the complex numbers, with the property that for any point in the space, the corresponding fiber is one of these objects that I'm trying to parameterize. And for any object that I'm trying to parameterize, there exists a corresponding fiber which is isomorphic to that object. There exists some S in S such that this pair is isomorphic to the corresponding fiber. So it's a very, very strong, it's boundedness in a very, very strong sense. And again, this number n and this number c are playing the role of the Hilbert polynomial. I do not need to know the whole Hilbert polynomial. I just need to know the degree of the Hilbert polynomial and the leading coefficient. Okay, so this is clearly a mouthful. So let's try and understand this result and its consequences a little bit better.
So this big letter C represents a set of rational numbers which satisfy DCC condition.
Yes, and our favorite example is the standard coefficients.
And you cannot have something which has two components of different dimension. It's not allowed.
Well, okay, so from the local definition of the singularities, the only way that could happen is if it's actually, you have distinct components that don't intersect each other, right? And in that case, you'd be okay if you have finitely many of these. You just sort of have two completely different modular problems. So. There may be some way of doing this in more general context, slightly more general context, but I wouldn't be an expert on that. So, okay, so.
Could you say what's I? The set C.
Oh goodness, thank you. I'm always unsure if calling it a set, it's an index set I or a set of coefficients C. So, any other typos that I can try and correct? Okay, I'm sure there will be more typos. Sorry about that.
Is that a typo over there?
You have to be more specific.
I'm just trying to slow you down.
Okay, so so maybe so a corollary, which I'm not going to prove now, but I will explain later on how to do it. So by a semi-continuity type of argument, there will exist some m such that m kx plus b is very ample for any semi-log canonical pair of this form. So once Collard's book is out, then this will tell you that the modular space of this semi-log canonical pair indeed exists and is a proper modular, a projective modular space, in fact. Okay. Another thing I wanted to mention is that it also follows another corollary. It shouldn't be immediate right now, but we'll see it later. Is that if I look, so it's not an immediate corollary. If I look at the set of volumes, let's say depending on n and c, these are volumes of all. So the volume, you can think of it, since the kx plus b is ample, you just take the top self-intersection. So we like to look at all the volumes where xb is some semi-log canonical model of dimension n, and as usual, the coefficients are in my set C, then this set satisfies the DCC. So there are no accumulation points from above, again. See, the difference between this set here and the previous set is the previous set I fixed the volume. Now, if I no longer fix the volume and I look at all possible volumes, then this, we have infinitely many possible answers, but it has some structure. It satisfies the DCC. In fact, more precisely, if we just consider the set of volumes where kx to the n, where x is a canonical model, then in fact this set is even better, it's discrete. So this looks like a very technical result. Why is it important or interesting? First of all, what does this mean? So in particular, this set here, since it satisfies the DCC and it's a set of positive rational numbers, or real numbers, then it actually has a minimum. In particular, volume and C.
Sorry, I'm getting confused, but the logic what you wrote.
Yes.
This conditional phrase, if this is discrete, is not related to the line above.
Okay, so
Where does the first sentence?
I should say, moreover, if I consider canonical models, so I specialize to a even more friendly, to a much more friendly situation, then the set of possible volumes is discrete. Thank you. So going back to the general case, one of the most important things that this tells you is that this set satisfies the DCC. It's a set of positive real numbers, so it has a minimum. Say v, little v of n, c. And so these volumes are always greater or equal than this minimum. So in particular, so you start with your SLC model.
But,
Go ahead.
but it could accumulate 0?
No, it's a DCC. There are no accumulation points from above. That's precisely the issue. Right? If it had no minimum, 0 would be an accumulation point from above. It's not a that's the whole content of the theorem, the corollary, which I have not proven. I'm just trying to illustrate the significance of the main result. So, for example, let's slow down just a second while Matsuki thinks about his objection.
No,
So-
I'm sorry, can I interrupt?
Go ahead.
So I was thinking about a surface case,
Okay?
quotient singularity. So therefore, it has like an index of arbitrarily high index.
Okay, let me make a remark that includes what you're saying. This is why it's so interesting.
Okay, I'm sorry.
Okay. So, dimension of x is equal to 1. This business about the volumes is trivial. Let's say x is smooth. Then volume of kx is just 2g minus 2. This is clearly discrete. Not a very interesting set. We'll do pairs xb in a minute. This is already non-trivial and interesting, and you've done this computation before, so this is not a new theorem for you, but it's a non-trivial computation. Okay, but let's look at dimension of x equals 2, again with no boundary. So if you look at when x is smooth, then the canonical class, or let's not say smooth, is canonical. Then canonical models do have singularities, but these singularities are mild. They're Duval singularities or rational double points. They're well understood. In particular, the class of the canonical line, the canonical class is Cartier. It's a line bundle. So Kx is Cartier. Therefore, Kx squared is a positive integer. Again, it's discrete. Okay, so now you're thinking of the log case. Maybe it's just easier to talk about dimension of x is equal to 3, where once again, now you have interesting singularities. Kx is not Cartier. It can have arbitrarily large index. Like, for example, think of the case of terminal singularities for simplicities. They're isolated points, and these points can have arbitrarily large index. So how does that match with this corollary that there's a fixed multiple m such that this class becomes very ample, right? This only works if I fix the volume, right? So these singularities of arbitrarily large index, it's clear that by if the modular space existed, it's clear by the semi-continuity argument that the higher the index, there are more and more components of the modular space, you have to move on to further and further components of the modular space. You cannot have infinitely many indices on one component of the modular space. Otherwise, it couldn't be a finite type by semi-continuity argument, right? So I think this is the kind of problem that you were worrying about. Let's now do the example of dimension 1 and log pairs. So you've probably never seen, well, it's rather easy, first of all. So what is the volume? So dimension of x equals 1. Then the volume of kx plus b is equal to 2g minus 2 plus the sum of these coefficients bi. It's just given by the degree of this class. Now, by assumption, the bi are in a DCC set. Any sum of numbers in a DC set is again in a DCC set. Easy exercise. So this is again in a DCC set. And this is discrete, so we're again in a DCC set. So the fact that these volumes are in a DCC set is first year undergraduate exercise. Do you understand what sequences mean? Now, specializing to a more interesting example. So suppose that your coefficient set is a set of standard coefficients. Then you've probably all done the exercise that in this case, the minimum volume of kx plus b is 1 over 42. How would you prove such a thing? Well, it's not illuminating. It's a case-by-case analysis. We already know that there has to be a minimum by what we've already observed. But how would you prove this? Well, you might as well assume that g is less than 2. Because if g is equal to 2, greater or equal to 2, then 2g minus 2 is greater or equal again to 2. This is a non-negative number. And so this is clearly, okay, I should have started by 2g minus 2 plus sum of the bi is greater or equal to this, which is clearly greater than 1 over 42. So I can throw away those cases. Now, if g is equal to 1, then I really have to look at this sum of the bi's because 2g minus 2 is 0. But now the bi's are of the form 1 minus 1 over k. So each bi is greater, is of the form 1 minus 1 over ki, greater or equal to 1/2. Since this is a non-zero number, this is greater or equal to 1/2, which is greater than 1 over 42. So now I only have to worry about the case g equals 0. Now, since each number is greater or equal to 1/2, it's clear, let's say this is I equals 1 to r, it's clear that r is less than 5. Because if I have 5 contributions, each one is 1/2, I will get 2g minus 2 is minus 2 plus 5/2, that's already greater than 1/2. So now you either have, it's also equally clear that r has to be greater or equal to 3. And so now you don't have many cases to worry about, and nobody wants me to see me go through the remaining cases and make a mistake. So I think that you can check that the solution 1 over 42 comes from, I think it's b1 is 1/2, b2 is, well, we factor that, right, 2/3, and b3 is got to be 6/7. Okay. And you probably saw this in the proof of the fact that if you look at the automorphism group of a Riemann surface or of genus G, then the order of this automorphism group is bounded by, not 42, 84 times G minus 1. So this is not a completely unrelated issue. So maybe I should corollary. So G greater or equal to 2. Then the automorphism group of a curve X is bounded by 84 G minus 1. Of course, it's always risky because I didn't prepare it, but what's the idea? Which can be made precise very easily. You look at the map from X, say, to X bar, which is just given by taking X quotiented out by this, the quotient of X by its automorphism group. Right, so it's a curve of general type. The automorphism group is finite. Look at the quotient. Then we have that K of X is, we call this map F, is the pullback of K of X bar. This is essentially Riemann-Hurwitz plus a divisor, sum of bi, bi, where these BIs are the form 1 minus 1 over Ki, where Ki is the local index of ramification. So once again, these standard coefficients are appearing in a completely natural way, and it's looking more and more unreasonable to try and work without them. Since this 2g minus 2 is greater than 0, then this degree had to be greater than 0. In fact, this formula tells you that 2g minus 2 is, by doing a degree computation, so that's the degree of this divisor. The degree of this divisor is, well, the degree of the map F, so the order of the automorphism group of X, times the degree of this log pair with standard coefficients. But since this number is positive, clearly this number has to be positive too. But now we've already observed, so this is what I call the volume above, right? This degree of volume is the same thing. You're just looking at the degree of this class. So now this is the minimum, so it's greater or equal to the order of the automorphism group of X times 1 over 42. So I take this 42 to this side. 42 times 2 is 84g minus 1, bounds the automorphism group of X. So this business that the volume has a minimum is an important one, and it's also important for log pairs. I should say that...
So the automorphism group of variety of general type in higher dimension, if you fix the dimension, the order is also bounded from above.
So a corollary of this result is theorem that if X of general type, then the order of the automorphism group, so I'm not assuming, let's say it's smooth of general type, I'm not assuming that it has canonical singularities, so then I won't measure it by the top self-intersection of the canonical class, but by the volume, which Barashian is the same thing. So this is bounded by some constant, depending only on the dimension, times the volume of the canonical class of X, where C1 is 42, and Xiao claimed that C2 is 42 squared, but the proof is hard to follow. There certainly is an effective bound that comes out of his work. If it's exactly 42 squared, it's a little, people are having a hard time following that. And for higher n, this is not known. It's non-effective. So I should say that this minimum of the volume, it's non-effective. I do not know how to compute it. Maybe let me make another remark. Even in dimension 3, X smooth, dimension of X equals 3, it's very easy to write down. There exists, I think it's due to Janov lecture, there exists a case of a surface of a freefold of general type where the volume of Kx is equal to 1 over 420. So you do have very small volumes. I think Chen plus Chen, so Alfred Chen and Meng Chen prove, I believe, something like the volume of K of X, I think it's 2200, but let's say is greater or equal to 1 over 2500 to be on the safe side. This is not optimal. I think conjecturally this is the right bound. So even for freefolds, we do not know what the optimal answer is. We know that there exists some lower bound for the volumes. We do not know what the optimal answer is. So the last thing to conclude that I wanted to mention here, going back to the general case of a semi-log canonical model with fixed volume. So those are the ones for which we want to construct the moduli space. We have to fix the volume, fix the Hilbert polynomial. Now suppose that we can break this up. So you can always break this up into its irreducible components. So as usual, f from this union of yi to x is the normalization. And as usual, I write kyi plus delta I for the restriction of the pullback of the canonical class of kx plus b to the yi. Then, if I denote by ci the volumes of the individual pieces, then you see it's really easy to check that the sum of these ci's is equal to c. But these belong to a DCC set, and this is a fixed number. So the upshot is we have finitely many possible CIs. So the number of components in which X can break up when you take the normalization is bounded. It's bounded by what? By C over the minimum of these volumes. And each one of these volumes has finitely many possibilities. There is a finite set of possible volumes. So what I'm trying to tell you is that if you're trying to construct modular space of these semi-log canonical models, you might as well try to construct the modular space of log canonical models, meaning normal varieties, with a fixed volume. Right? The individual components have fixed volume and hence fixed Hilbert polynomial. So I'm out of time now. Next time, I'm going to start with actual definitions and discuss things like multiply ideal sheaves and the singularities of the canonical model, and hopefully by the end of next time, get to start proving the first cases of this result. So I'll start by proving simpler versions of this result, and then I will build up to the final version because there's a whole bunch of different ideas, and I don't want to introduce them all at once. It will be much more pleasant if we sort of try to conquer each technical issue one at a time. Thank you.